Ok, pues vamos a empezar este tercer coloquio de cómputo cuántico en el Centro de Investigación en Computación. Le quiero dar la más cordial bienvenida a todas las personas que están conectadas vía remota en esta sesión. Es nuestro tercer coloquio de cómputo cuántico en el Centro de Investigación en Computación del Instituto Politécnico Nacional. Me gustaría presentar a las personas que en este momento nos acompañan en un presidium virtual y que nos darán algún mensaje de este tercer coloquio de cómputo cuántico. En principio, me gustaría presentar al doctor Irán Castro Calvo, director de nuestro Centro de Investigación en Computación del Instituto Politécnico Nacional.
Muchas gracias, doctor. Muy buenos días. No sé si me escuchan correctamente.
Sí, doctor Irán, muchas gracias por estar aquí con nosotros.
Igualmente, muchas gracias.
Me gustaría presentar al maestro Samuel Pérez Rodríguez, representante de la Secretaría de Investigación y Posgrado, en representación de la doctora Laura Arreola. Maestro Samuel, bienvenido, buenos días.
Muchas gracias, muy buenos días.
Muchas gracias, maestro Samuel Pérez. También me gustaría presentar a la maestra en Ciencias Catalina Albornoz, de la empresa Xanadu. Buenos días, Catalina. Gracias por estar aquí.
Gracias por la invitación. Buenos días.
Me gustaría también presentar es un honor para mí presentar al doctor Humberto Sousa Azuela, profesor emérito del Centro de Investigación en Computación del Instituto y jefe del Laboratorio de Robótica y Mecatrónica. Doctor Humberto, buenos días, bienvenido.
Buenos días a todos.
Y finalmente, quien ha hecho posible todo este evento con gran esfuerzo, le ha dado mucha dedicación al evento. Me gustaría presentar también al maestro de Ciencias Alberto Maldonado Romo, alumno del doctorado del Centro de Investigación en Computación, y pues quien ha trabajado arduamente para este congreso. Bienvenido, Alberto, buenos días.
Buenos días, doctor. Gracias a todos por venir.
Muy bien, pues una vez hecha esta presentación, me gustaría pedirle a Alberto si nos da su mensaje para este tercer coloquio. Por favor, Alberto, adelante.
Muchas gracias, doctor. Sí, me gustaría agradecerle a todos por su asistencia, a los directivos del instituto, al doctor Humberto, a mi doctor y asesor, doctor Yalja, al director del CIC, Gran Calvo, a los directivos del CIC, que nos dieron posible este evento con su apoyo, por el apoyo de igual de Alejandra y de Paulina, que nos ayudaron en su momento, que igual Vanessa, la parte de difusión, que me enseñaron mucho sobre esta parte, ya que me gusta mucho compartir lo que es la computación cuántica en diferentes aspectos y generar un coloquio a un nivel internacional por parte de Latinoamérica para mí es un honor. Tratar de apoyar en este tipo de herramientas, cómo se puede utilizar la computación cuántica actualmente en la ciencia y tecnología. Discutiéndolo con Catalina, igual estuve con este apoyo de cómo tratar de comunicarse de manera con otros estados o países y compartir estos conocimientos, ya que no es algo muy fácil acceder como latinoamericano o hispanohablante. Y este evento a mí me gustaría compartirlo y tuve la oportunidad de que muchas personas que considero amigos, colegas, que me están apoyando en este evento, que accedieron de una manera muy positiva y que con este evento podemos compartirlo con personas que les gustaría aprender sobre computación cuántica. Y ese es el motivo de este evento, generar que las personas sepan más sobre computación cuántica, qué es lo que hay, qué es lo que existe, y cómo podemos apoyarlos en esta parte. Y también invitarlos de que este evento es un pequeño paso o un primer paso que podemos tener e interactuar con la computación cuántica y tratar de conectar con más personas, con las personas que están como expositores y posiblemente crear no solamente una maestría o una tesis, sino colaborar con ellos en un futuro, trabajar con ellos en la empresa, ya que muchos expositores son parte de una industria que están generando proyectos de investigación, de innovación en computación cuántica. Yo creo que esa es una gran oportunidad para interactuar con ellas, con esas personas. Muchas gracias, doctor.
Muchas gracias, Alberto. Pues sí, efectivamente, el tercer coloquio es todo lo que acabas de mencionar. Y también nos gustaría ahora que pues, una persona que ha estado en el centro de investigación desde sus inicios, que ahora es profesor emérito del Centro de Investigación y Computación del Técnico, jefe de laboratorio de robótica y mecatrónica, y pues que ha sido también uno de los impulsores de este evento, pues que nos dirigiera un mensaje al respecto de este tercer coloquio. Le pediría al doctor Humberto Sosa Azuela si nos puede pedir un mensaje. Adelante, doctor.
A ver, quiero saber si alguien me está escuchando. Es que me hace así, pero no sé si el público lo está escuchando. Quiero que se lo sepa. ¿Ya ahora sí? Ok. Bien. Antes que todo, muy buenas tardes, muy buenos días, más bien a todas las personas que nos acompañan. Hoy es el día en el cual empezamos nuestro tercer coloquio de cómputo cuántico. Y déjenme encender mi cámara. ¿Qué dice el día en que iniciamos nuestro tercer coloquio de cómputo cuántico? Nos sentimos muy orgullosos por organizar este tercer evento en el cual vamos a tener la oportunidad de compartir con ustedes lo más reciente a nivel nacional y a nivel internacional con exponentes de la primera calidad sobre los últimos avances que se están haciendo en algunas de las temáticas más importantes alrededor de este fascinante campo de investigación. Quiero agradecer a todos mis colegas organizadores, en primer lugar al doctor Francisco Irán Carlos Castro, director de nuestro centro de investigación, por el invaluable apoyo que nos da para organizar este evento. De igual manera quiero organizar al doctor Juan Carlos Chimal Guía por su siempre disposición para poder organizar. De hecho, con él fue el que se organizó el primer evento. Muchas gracias, Juan Carlos, por apoyarnos siempre. Quiero agradecer también a Jesús Yalcamón Pierre Pérez por la disponibilidad, por estar ahí siempre para que este evento se organice. Y más allá de todo eso, quiero agradecer a Alberto Maldonado, que ha sido, en mi opinión, el principal motor e impulsor de estos tres eventos que ya en este momento pues, nos encontramos en el tercero. Estoy seguro que a lo largo de estos días ustedes van a poder disfrutar y van a poder compartir con otros colegas acerca de los más recientes avances. Yo solo espero que este evento sea de provecho para ustedes, sea un foro en el cual se convierta en un catalizador de intercambio de ideas entre todos nosotros. Muchísimas gracias a todos.
Muchas gracias, doctor Humberto Sosa. Es cierto, definitivamente el intercambio de ideas es algo fundamental que tenemos en mente cuando hacemos esta clase de eventos en particular. con el coloquio de cómputo cuántico. Y en esta ocasión, una pieza fundamental ha sido la incorporación de algunas industrias. La parte del sector privado ha sido interesante. Alberto, durante su formación ha conocido gente interesante en el sector. Y en esta ocasión nos gustaría invitar a Catalina Albornoz, que es la empresa Shanaru, que nos pudiera dirigir un mensaje, porque es la primera vez que una empresa está en este coloquio. Entonces, adelante, Catalina, si nos pudieras dirigir el mensaje.
Muchas gracias por la invitación. Escucho un eco, no sé si los escuchan todos. Creo que hay 2 micrófonos abiertos en la sala en la que están ustedes. De pronto sí, eso. Perfecto, ahora sí. Primero quería darles muchísimas gracias por la invitación aquí a dar unas palabras. De pronto si el doctor Humberto Sosa se pone en mute, ahí yo no escucho eso, perfecto. Hace unas semanas hablaba con un colega que trabaja en otra industria en España y él me comentaba que siente que por ser de Latinoamérica tiene más dificultades, tuvo más dificultades para llegar a la industria. Y me dejó pensando, porque lo que dificulta, digamos que a veces el proceso no es el pasaporte, no es la visa, ¿sí? Las empresas buscan talento, las empresas están locas por buscar talento, personas excelentes. Entonces, ¿qué es lo que a veces vemos como una dificultad? No es el pasaporte, no es el apellido y no es la cara, ni siquiera la miran. Por favor, no pongan foto en las hojas de vida. Lo que falta es networking muchas veces. Nos falta conocer otras personas que están en el campo, ¿sí? Y que están haciendo cosas o parecidas o diferentes a lo que hacemos nosotros. Así que este evento va exactamente al grano, al punto de lo que se necesita en Hispanoamérica. Y entonces le agradezco mucho a Alberto Maldonado por impulsar la comunidad de habla hispana, porque estos eventos realmente que hacen la diferencia. Estos eventos hacen que se conozcan personas que están trabajando en industria y academia y que a futuro puedan llegar a esos ámbitos internacionales en el país donde sea. Así que los invito a continuar este legado con los coloquios. Es una excelente iniciativa para trabajar en que se comparta el conocimiento, pero también hacer networking y conocer a las personas que el día de mañana estarán trabajando en una empresa y nos van a avisar si hay una convocatoria, por ejemplo, o si están buscando un estudiante de doctorado en la academia, o si hay una posición para profesor. Entonces, estas redes que hacemos, las redes que harán todos durante el coloquio, van a ser fundamentales en el desarrollo de las carreras de todos los asistentes, sea tanto en academia como en industria. Y entonces va mucho más allá del conocimiento compartido y se va hacia las relaciones interpersonales que se crean. Por eso, entonces, nuevamente felicito a los organizadores, al Centro de Investigación en Computación por abrir el espacio para que se den esta creación de redes de networking que ayuda entonces al avance personal y profesional de cada uno de los asistentes. Muchas gracias nuevamente por la invitación y espero que con eso en mente también aprovechen aún más estos días de coloquio.
Catalina, por estas palabras. Curiosamente, cuando se inició el primer coloquio, la comunicación era académica entre pares, pero esto ha crecido demasiado y creo que las palabras de Catalina son muy valiosas en el sentido de networking, poder establecer esa colaboración con todas las áreas, no solo la parte académica. Pero en la parte académica, desde el inicio, ha sido fundamental el apoyo del Instituto Politécnico Nacional. La Secretaría de Investigación y Posgrado, desde el primer coloquio, se ha mostrado muy interesada en difundir esta clase de eventos, en particular esta punta de la ciencia, ¿no? de la investigación. Y para ello me gustaría invitar al maestro Samuel Pérez Rodríguez, de la Secretaría de Investigación y Posgrado, que nos dirigiera un mensaje al respecto. Adelante, maestro Samuel.
Gracias, muy buenos días a todos. Me da mucho gusto que no pierdan el ímpetu y continúen impulsando eventos de colaboración académico y con la industria, ¿no? Tengo entendido que se quedó en pausa esta tercera edición por situaciones de la contingencia, y retomarlo recién en este 2022, cuando las actividades se han vuelto un poco más ya en una adaptación a la situación, a las circunstancias que tenemos en el país y a nivel global, ¿no? Entonces, en ese sentido, quiero externar una felicitación e invitarlos a continuar impulsando la interacción de los estudiantes con la industria. Es importante no perder de vista el sentido de la formación de los estudiantes de posgrado del Instituto Politécnico Nacional. En ese sentido, el Centro de Investigación en Cómputo es un centro de investigación líder en el Instituto Politécnico Nacional. Lo vemos reflejado en sus programas de posgrado consolidados a nivel internacional, en la amplia oferta educativa que tienen, en los diversos y numerosos proyectos de investigación impulsados desde la Secretaría de Investigación y Posgrado. En ese sentido, les externamos una felicitación y de igual manera, pues, a los profesores, al doctor Irán Calvo, al doctor Sosa, compartirles esta importante interacción que se debe tener con la industria. Muchas gracias por el espacio.
Muchísimas gracias, maestro Samuel Pérez, por sus palabras. Y sí, efectivamente, el apoyo del instituto, transmítale a la doctora Laura Arreola, pues ese apoyo que siempre hemos tenido en el Centro de Investigación para esta clase de eventos. Y recuerdo que la primera vez que fuimos a hablar con el doctor Irán Calvo, director del Centro de Investigación, pues inmediatamente nos dio la luz verde para poder hacer este evento. Definitivamente, el doctor Irán siempre ha sido un impulsor de esta clase de cosas, de este tipo de coloquios, de congresos, de ideas innovadoras, intentar estar a la vanguardia en la educación. Y pues le agradezco mucho al doctor Irán Calvo su apoyo, y nos gustaría si nos puede dirigir un mensaje para empezar los trabajos de este tercer coloquio de cómputo cuántico aquí en el Centro de Investigación. Adelante, doctor.
Claro que sí, muchas gracias. Muy buenos días. Buenos días a todos. Es un gusto para mí poder estar aquí con ustedes. Sobre todo agradezco la presencia de maestro Samuel Pérez Rodríguez en representación de nuestra secretaria de Investigación y Posgrado, la doctora Laura Arreola, a quien enviamos nuestras más cordiales y afectuosas consideraciones. Enviamos un gran saludo y agradecimiento, como siempre, por el apoyo a estos eventos. Asimismo, me permito saludar al doctor Juan Carlos Chimal, quien ha apoyado mucho, así como él nos comenta, pues también sin su intervención no sería posible todo esto que ha estado realizando. Agradecemos la presencia de Catalina Albornoz, quien ya nos ha comentado un poco de cómo está la situación por allá y que ha sido pues muy importante que ella se encuentre por aquí apoyando, contribuyendo y sobre todo fingiendo como este enlace tan importante, ¿no?, entre academia, industria y pues, el conocimiento que se requiere para poder integrarse para poder tener soluciones productivas adecuadas que sean útiles en la aplicación de todo este conocimiento que se genera también a nivel teórico en nuestros centros. Agradezco mucho también la presencia del doctor Humberto Sosa, quien ha fungido también como un fuerte impulsor de no solamente el cómputo cuántico, sino en general. Pues sobra decir todo lo que podríamos comentar de él. Él es ampliamente conocido por una gran diversidad de trabajos, tanto en esta área como en el área de robótica. Y por supuesto, al respecto, agradecerte muchísimo toda esta iniciativa que has tenido desde el principio, que te acercaste a nosotros. Como comenta el doctor Chimán, me pareció una excelente idea, algo que pues valía la pena llevar a cabo, algo que de estos proyectos, ¿no? Que no solamente se quedan en una sola iteración. Como ya vemos, hemos estado realizando esto pues ya por tercera ocasión. Esta sería la tercera vez que se está realizando, y pues siempre con este gran impulso, con este gran empuje que tú le has dado, Alberto. Entonces te felicito, agradezco pues esta iniciativa, y pues que en combinación, conjunto con todos nosotros, con el apoyo que de mi parte, del lado de la dirección, pues siempre tendrás, y por supuesto el apoyo del doctor Chimal, que está siempre al tanto de pues estas cuestiones tan importantes, ¿no? Para el desarrollo de la computación, para el avance, para aquello que nos permite estar a la vanguardia, para no quedarnos nada más en la computación clásica, no porque no sea buena, no porque no funcione, sino porque siempre tenemos que ver más allá. Y sobre todo también compartirnos este entusiasmo, como nos platicabas en tus palabras del inicio, es algo que te gusta mucho, y cuando hacemos algo que nos gusta, lo transmitimos. Logramos que este gusto propio se extienda hacia otras personas, que otras personas a lo mejor que no han oído tanto de cómputo cuántico se involucren, lo conozcan, vean que no muerde, vean que es algo con lo que se pueden hacer grandes cosas. Y pues todo esto, pues gracias a eventos como este, ¿no? Entonces, en suma, les agradezco mucho a todos esta iniciativa, que ahora de manera conjunta podamos nosotros estar llevando a cabo este inicio del tercer coloquio de cómputo cuántico. Entonces, doctor, no sé si me permite dar una inauguración formal, un inicio formal. Muchas gracias, doctor. Entonces, siendo las 9:56 del día 28 de noviembre del 2022, damos por formalmente inaugurado el tercer coloquio de cómputo cuántico. Muchísimas gracias, y pues disfrútenlo mucho.
Pues ya siendo inaugurado el coloquio, pues les agradecemos a todos que se hayan conectado a esta ceremonia de inauguración. Los invitamos a todos a que disfruten el evento, como dijo el programa. Fue diseñado específicamente para todos ustedes. Vi conectada gente quizás extranjera. Lo hicimos en español, pero I would like to thank everybody who is connected to this ceremony of inauguration. I would like to thank everybody. This event is for all of you. Enjoy it. Thank you very much. Y gracias a todos. Los dejo entonces ahora con la primera presentación. Adelante, Ángel, creo que va a ser nuestro comandante virtual. Estén bien. Saludos a todos.
Muchas gracias, doctor. Bueno, Lía, ¿are you ready?
Lía, are you there?
Hello. Hello. Okay, wait a second. I will present you. Ok, bueno, vamos a empezar con la primera conferencia de este coloquio, la cual va a ser dada por Lía Ye. Lía Ye es una estudiante de doctorado en Oxford, en el grupo de cómputo cuántico. Ella tiene un grado en física por parte de la Universidad de California, y actualmente se encuentra trabajando en Quantinum. Later, yeah, when you're ready.
Hello, everyone. Thank you to the organizers for organizing this. So especially thank you to Alberto for all the immense effort it takes to organize a colloquium and hackathon and workshops, a whole week of workshops before that on such a scale. First I will introduce myself. I am a PhD student at the University of Oxford, and today I'll give a talk. It's an overview of the research that I do in my group, and also in my recent weeks I started working part-time at Continuum. So this presentation will go over both the work that I did in a year working part-time at IBM Quantum Education to teach quantum computing and quantum circuits using the ZX calculus, and my PhD research, which applies these diagrammatic methods in order to reason about qubit quantum computation. So first, can I check, is my screen being shared properly? I believe so. Okay. Alberto or someone, can I ask, is my screen sharing properly? Do you see my title slide?
Yes, the screen is sharing virtually. I don't know if in the room.
Thanks, Catalina. Okay. In that case, I'll begin. The title of the talk is Compiling Q-Controlled Clifford plus T circuits and Controlled Phase Gates with the ZX calculus. Starting off, the tutorial that I worked on as my project at IBM Quantum Education in the past year, it's available as a PDF at this GitHub link. And the current plan and the plan is to put it up on archive for anyone to access to read as a PDF as well. Right now, it's still in a draft phase. The draft is almost complete, but any kind of feedback I would really appreciate. And an overview of this tutorial is that the idea of it is to teach quantum computing using diagrams. This means to learn what they mean mathematically, and what every diagram means something mathematically. So it could be a matrix, linear map, and you can write any quantum circuit in the ZX calculus. But this tutorial not only covers the ZX calculus, it also covers an intro to quantum computing, including matrices, bracket notation, the unit circle, block sphere, and the block sphere. So this is possibly a good add-on or a companion or a separate learning material to a textbook that I believe is being launched today by Bob Kuka and Stefano Goggioso. That's an intro to quantum computing using diagrams that's intended for high school students. So the tutorial I wrote, it's nearing 100 pages. It has a prerequisite knowledge of knowing matrix multiplication, complex numbers, and basic probability. Then it's targeted towards people with a high school degree, maybe from more of a software development standpoint. And the goal is to starting off from what is a qubit at the beginning of the tutorial. By the end of the tutorial, it will go through quantum teleportation as a protocol in the ZX calculus. I'd like to acknowledge James Weaver at this point, who is my collaborator at IBM Quantum Education. He's a quantum developer advocate at IBM. So, as an intro to ZX calculus, hopefully this comic style or drawing can be friendly. The first diagram rewrite in the tutorial looks like this. So it is reading these diagrams from bottom to top. This, you have a light bulb in the on state. And then you can also test by having an upside down, the vertical reflection of that triangle, have it be a test of asking whether or not is this light bulb in the on state. And if that's true, then the probability for that that the probability of the test is true will be on this right-hand side of this equal sign. So in other words, this is a diagram with, on the left-hand side of the equation, that has no inputs and no outputs. So it's a number, and it has a number. So here on the right-hand side of the equation, you have the number 1. And so far, we've just had state and test. In quantum, you would call them effects. Sorry, I'm getting a bit of echo. Can I ask someone to mute? Thank you. In the top right, so you have, if you have an off light bulb and you have a process that's light switch, we write these as processes because they have one or more inputs and one or more outputs, reading from bottom to top. And if you flick a light switch when the light bulb is off, then the light bulb will become on. This goes back from Penrose's tensor notation, and the ideas of using diagrammatic notation in math goes back a very long way. So what you can do, why this is useful, is that equation substitutions actually here become rewriting parts of diagrams. So here at the bottom leftmost, you first have inside this dashed gray box, you have the equation, the left-hand side of the equation on the top right of the screen. So if you have an off light bulb and then you flick it to on, and then you test if the light bulb is on, then you apply the rewrite rule on the top right of the screen right now, and you get the equation on the top left of the screen. So you see that you prove a new diagram equation here by applying and substituting rewrite rules, diagrammatic rewrite rules that you already have. So this idea goes into quantum computing because you can, with a few rules, you can derive all other rules needed for proving equalities of quantum computations in qubits. So the ZX calculus has succeeded in this result a few years ago, and we recently succeeded in this result for a qubit version of ZX calculus, well, ZXW calculus. That paper isn't out yet, but it's quite exciting to be able to, with a few rules, be able to derive all other rules. So the basis states to show how every single state in Brock annotation, all the Z and X basis states of a qubit in Brock annotation would be drawn in ZX calculus. Here I use green and pink, but I may use green and red in other slides here. It's as long as they're distinguishable. So here the Ket0 state is just a pink spider with reading from left to right, just like in circuits. This has 0 inputs and 1 output. And the Ket1 state is the same thing, but now it has a pi label on the pink spider. The Ket plus state is the same thing as, but now green, and so same with the Ket minus state. You also have phase gates, and so far this just looks like new notation for a phase gate, where you have a green spider for a Z phase gate that's labeled with the phase rotation alpha. So on the right-hand side here, you have the block sphere, and this block sphere just shows the Z. You can see, visualize that the Z rotation gate is a rotation of angle alpha about the Z axis on the block sphere. And you do the same for the X phase gate, which is a rotation about the X axis on the block sphere. So here I introduce one rule, our first rewrite rule on the ZX calculus in this presentation. So here, if you do a phase gate, but the phase rotation is 0 degrees, so you're rotating an angle of 0, it means it's the same thing as if you did the identity operation. So in other words, if you have a green spider, but there's no label, we by default, the label is a phase of 0 if there's no label, then you can just remove that green spider from the wire, just like this. And same with the corresponding X rotation gate spider. They're called spiders because they can have multiple legs, and we'll see some examples of that shortly. Hello, sorry, I'm having a call. So on the bottom right, here we can see an application of these another rewrite rule. So here, this is just what happens if you apply first the X gate to the ket0 state, and what you do is get the ket1 state. Correspondingly, if you apply the Z gate to the ket plus state, then you get the ket minus state. And something you can observe here is that when you use this notation, what this is doing to the diagrams in order to get the right matrix computations is that you're fusing these two same color spiders that are connected by at least one wire. And so this holds more generally if you have two spiders with any number of legs, as long as they're connected by at least one spider and they're the same, one wire and they're the same color, you can fuse them together and add their faces together. So here's a comic I drew on an airplane about this for the green spiders. And here's another comic for the pink spiders. These comics are not in the tutorial yet, but I'm going to put them in before it's on our card. So in the first example of a spider with multiple legs, here is a CX gate, such as your normal qubit CX gate. And in ZX, this is notated where the control is a green spider with 3 legs and the target is a red spider, or this is pink. What I used earlier is pink, but I didn't change the colors for this side. This pink spider with 3 legs. And something you could do is, and I'll show on the next slide why this works, is partially explain why this works, is that you can think of this as first a green 1 input 2 output operation followed by a red 2 input 1 output operation, but it's mathematically equal to treat it as this red 1 input 2 output operation and then a green 2 input 1 output operation. And what these specific operations are on the Z basis states. So this is the computational basis states. So here A and B are bits. So these states are either ket0 or ket1. What the green spider does to ket0 or ket1 is that it copies it. Whereas what the red spider with 2 inputs and 1 output does to these ket0s and ket1s is that it takes their XOR, which is the same as addition modulo 2. So bitwise addition, or XOR. And if you look at this with a CNOT gate that we had earlier, then here in the middle of the slide, starting from the left-hand side, going to the right, if you plug in ket0 to the control of a CNOT gate, you can first do the copy rule to copy that ket0. Then you can use the spider fusion rule to fuse the bottom of the 2 copied ket0s to the target spider, like red spider, and then you get you get the proof that it's an identity gate on the target when the control is ket0. And you can also do this to the target as well with the ket plus state. So this is really cool. With this notation, it's really clear to see that if you apply the ket plus to the target of the CX gate, then the ket plus will copy through the red spider, and then you can fuse it with what we call the control, but actually it's showing that the CX gate acts in the opposite direction in the opposite basis. And so you get ket plus on the target, what we usually call the target wire, and you get identity on the control wire when you feed in a ket plus to the target of a CX gate. And so one thing I'd like to emphasize here is that what's attractive about this diagrammatic notation is that not only is it a bit user-friendly, I hope, but also and intuitive, but also you don't need to work with the matrix multiplications explicitly in order to do these reasonings. But you always are doing these matrix properties underneath. So every diagram here has a matrix meaning, but you don't need to compute the explicit matrix every time. Another rule I will show is that, first of all, any square by convention, I made them blue, but you may also see them as yellow squares. But these squares, which have 1 input and 1 output, that's the definition in the ZX calculus of the Hadamard gate, or just how that's drawn. And if you have any pink spider with any number of legs and you put a blue square on every single one of those legs coming out of the spider, then you can change that whole thing to a green spider of the same face. And the same goes in the opposite direction. If you have a green spider with all blue, all squares, so all Hadamard gates on all of its legs, you can, and then change that to a pink spider of the same face. We call this the color change rule, and basically this captures the intuition that these Hadamard gates are quantum Fourier transforms. And so when you, as an application of all these rules we went so far, if you take, this is a Bell measurement, so you do a C0 gate, then a Hadamard gate, then measure 2 bits. First of all, if you convert every single one of these gates and measurements to the ZX calculus, this is the diagram that you get. But you can then simplify in the ZX calculus what the Bell measurement is, and you can go beyond what you could do with only the circuit notation. So, for example, this steps of this simplification, if you just see how as far as you could simplify, you can first do the color change rule by applying the Hadamard to the A pi. So A is a bit, so it's either ket 0 or ket 1 measurement result. Then you can do spider fusion to get this thingy. And you can slide these around, and I will talk about the sliding a bit later. But you get a kind of 180-degree wire bend and a Z up, maybe a Z gate or an X gate, depending on what A and B were measured as respectively. For example, specifically when the 1 in 4 chance when A and B are both 0, as A and B are both independent bits, then it reduces to, because A pi is 0 and B pi is 0, and you can remove spiders with 0 phase because it's just rotating at an angle of 0, then you just get a 180-degree bend of wire. What this is useful for is, here's a comic, call it wire bending. And if you have wires bent in this shape, you can pull them to be straight. And actually, this was even in Rick and Morty, one of the episodes on the snake scientist blackboard. So diagrammatically, what this looks like is that you, for example, this dashed gray box area of this equation on the left-hand side is a Bell state. And if you pull this straight, and you have a Bell measurement where you measure both outcomes be 0 on the top, and then if you pull it straight, you get a wire. And more generally, you can bend wires however you want. So this example is that saying the left-hand side of this equal sign and the right-hand side are equal because all their connections are the same. And as long as all the inputs and outputs and all the connections are the same, you can bend the wires. And this means, for example, that you can slide any map, so any process, any process with at least one input and output around these bends and take their transpose. So here on the right-hand side, you can see that if you represent a normal process, a process labeled by a box F with a trapezoid, the transpose is turning around 180 degrees. The complex conjugate is a horizontal reflection when you're reading the diagrams bottom to top or top to bottom. And the adjoint or conjugate transpose is the vertical reflection. So like the ket to the bra or the bra to the ket, for example, that's a vertical reflection. And you can also, this gives a diagrammatic intuition of the transpose because you're swapping the inputs and the outputs. You're turning the inputs into outputs and turning the outputs into inputs of your map. So that's why you can represent transpose as a 180-degree rotation. Here, lastly, for this overview of the tutorial, and this is a spoiler of where the tutorial goes, but the tutorial is much more in depth as the tutorial Intro to ZX Calculus that is up on, that I linked on GitHub, is it's almost 100 pages. So it goes to these things much more slowly and with many examples. in explanations. But there's a bit of spoiler. So on the left-hand side, you have, on the top left, you have the normal circuit model diagram for a quantum teleportation circuit. This circuit diagram was made by Alberto, so it's very pretty. And the protocol for quantum teleportation would be that Alice has a state ket psi, and Alice wants to send the information about what is that state to Bob, or send the copy of that state to Bob. But in quantum, you cannot copy information. But anyway, so this is the protocol. Alice and Bob share a Bell state, and with that, Alice can do just a measurement on on these 2 qubits that she has, and then Bob will automatically get psi with some errors, and if you correct those errors, then Bob will perfectly get that copy of that state. So on the bottom left, first, if you were to write this in ZX, just take every single part of the diagram, every operation in that protocol, and write it in ZX, just convert it as we did before. And then on top right, we already saw from before what a Bell measurement is in ZX calculus, and then the Bell state is the same thing, but the horizontal reflection of that. So that's it. But in the Bell state, you know that the 2 input bits were ket 0. So you know that what you can do next is that you can slide these errors that you get from the Bell measurement and over, and these correction steps, Alice calls Bob and says what her measurement results were, and then Bob applies the corresponding correction. So applies an X gate if Alice measured A to be 1, and doesn't apply the X gate otherwise, and same for Z. Then what you can prove in ZX is that by fusing these adjacent A pi's and these adjacent B pi's, then in removing them, because it's addition mod 2, then Bob gets a copy of Alice's original state ket psi. And so this shows as a proof in ZX that you can, that the quantum teleportation is doing what it's supposed to. So to take a breather here, in the rest of this talk, I'll go over an overview of my PhD research on qubits and qubits in the ZX calculus. So I will note there wouldn't be time to go over a lot of the details, but I will do my best to give an overview, and do feel free to ask me any questions afterwards via Discord or email if you have questions on specific of the details. To start off, what a qubit is qubits are physical systems of dimension d equals 2, that 2-dimensional quantum systems, and qubits are 3-dimensional quantum systems. So qubits, instead of just ket 0 and ket 1, it also has ket 2, and this ket 2 state is already available in quite a few of the qubit devices today. For example, this is transmon. This is the energy diagram of a transmon qubit. As you can see, because it's just a non-linear oscillator potential, you can have higher energy levels. So they already exist in qubit devices. It's just that the calibrating of those gates is a bit tricky. So, but people are working on that. What qubits could be good for? To give some examples, you could do some hardware tricks to make the leakage error of your qubit operations less if you take advantage of the qubit states. You can do some qubit algorithms. You can do emulation. So this is doing some, you might get some more efficient gate counts if you do qubit gates but using qubits. So use the qubit subspace, or so restrict, if you just look at the 0-1 input parts of the some qubit gates. Why fault tolerance for qubits could be useful? So many people believe that you need fault tolerance on quantum computers to do these long-term quantum algorithms that we would want. And So the Clifford fragment is the fragment of quantum computation that is efficiently classically simulatable, and these Cliffords also generalize to any prime dimension qubits, sometimes called qubits. So just P for prime. But while Cliffords are efficiently classically simulable, we can efficiently simulate them with classical non-quantum computers, but it's not universal. You can't do universal quantum computation with just Cliffords. So the specific way that Cliffords generalize, if you apply the prime dimension qubit generalize, or just qubit generalization of poly X, D times, then you get the identity, and same with Z, apply Z gate D times. And you still have your Hadamard gate in qubits, and you also get these things called Weyl braiding relations here, which is what the phase of omega, where omega is the dth root of unity, so e to the 2 pi I over d, where d is the qubit dimension. You get a factor of omega when you commute x and z. You also get a Clifford hierarchy in prime dimension qubits. So if we say that polys are the first level and Cliffords are the second level, then you can generalize this to the nth level, regardless of qubit dimension, where the nth level is such that if you conjugate it with any unitary, such that you conjugate it with a poly, and the correction needed is in the n-1th level. So this is, for example, interesting if you're injecting certain non-Clifford states into your circuit. What kind of correction do you gate? What kind of level is the correction gate? For qubit polys, here are some the precise definitions. So X, just like in qubits, this is also true in qubits, but in general, when you apply X gate to some computational basis state K, so K is any integer from 0 to d-1, then X is the +1 operation mod D, and Z is the omega to the K operation mod D, where omega is the dth root of unity. So for qubits, this is just exactly your familiar gates with these matrices. And for qubits, this is what the matrices look like. With these generalizations, I studied this because I was motivated to study this because I felt that I'll realize a lot of the existing large multi-qubit gate decompositions were not in a way that could be fault tolerant. So here are the definitions of the qubit X basis states and the qubit Z basis states, where omega bar is the complex conjugate of omega, which is equal to omega squared. To show some notation for qubits, you can have the CNOT gate for in qubits. If you have a Ket2 controlled X+1 gate, this means that you apply the X+1 gate only if the control is in the Ket2 state, and you apply identity to the target qubit if the control is in the Ket0 or the Ket1 state. So this is a non-Clifford gate, this Ket2 controlled X+1. Whereas this is Clifford, this lambda controlled X+1 gate is Clifford for any qubit dimension. So, and it's you apply X+1 mod 3 if its control is Ket1, and you apply X squared, which is X-1 mod 3 if the control is Ket2 for qubits. And you also have its inverse. So notably in qubits, there are 5 reasonable types of generalizations of these X gates. So on the left, these two are poly. It's the X+1 mod 3 and the X-1 mod 3. And on the right-hand side, these 3 are Clifford. So it's the X gate that swaps 0 and 1, but keeps 2, doesn't change Ket2 state, or it can send Ket1 to Ket2, Ket2 to Ket1, and be identity on the Ket0 state, for example. All these permutations. So these are all the possible permutations you can do on qubits, on a single qubit basis states. So to add one more reason to fault tolerance for qubits, you can add a non-Clifford gate for universality and conceivable fault tolerance. So you just need at least one non-Clifford gate. And it'd be better if it supports magic state distillation, and then you can inject it into your circuit. So for Qtrits, there are two, I've seen in the literature that there's two main candidates that were considered for a single one Qtrit non-Clifford gate. So the Clifford plus T gate set means that you add to the Clifford gate set this T gate with this matrix, and the Clifford plus R gate set is the R gate with this matrix. And so the T gate is in the third level of the Clifford hierarchy, while the R gate is nowhere in the Clifford hierarchy. To show an early example of emulating qubits using Qtrits, you could do, in 2019, Pranav paper and collaborators' paper showed that you could do a log def qubit Toffoli without using any ancilla, just using Qtrits. And to also show, I found if you could do a binary AND gate with T count 3 and Qtrit Clifford plus T with this decomposition. And in qubits, it's not possible to do the AND gate on 2 qubits because it must be reversible. But for Qtrits, you use this 2 state as a trick. You could do store some additional memory inside the computation. So here's the truth table of that gate, but these blue rows are the parts that is when the inputs are bits versus so the inputs are bits, and then the output is also that you care about is also a bit. You could also do a qubit CCZ gate with Qtrit Clifford plus R with R count 3. So as far as I know, this is the lowest number of single qubit gates, non-Clifford single qubit gates needed to do quantum, so qubit Toffoli. I'll skip some forthcoming work, so in the interest of time, but what I want to show is the gist of it would be this slide. So you get a lot of the things that you can write down in qubits EX calculus do extend to any prime dimension. So this copy operation, which was what we saw in the qubit CX gate, also shows up in the prime dimension qubits as in their CX gates, actually all dimension qubits. And then you also have the addition mod D operation. And so this CX gate in this, I use this notation on the left, but for a circuit model, but on the right-hand side, it just looks the same it's the same drawing. You just interpret it in a different qubit dimension. You can still do spider fusion in any qubit dimension, and you can also do this color change rule. Recently, so this summer, there was a paper on completeness of ZX calculus for prime dimension qubits, the Clifford fragment. So these are all the rules that's necessary for that. So the 2 I showed on the previous slide are circled in the top left. And so if you have any 2 prime dimension Clifford circuits that have the same underlying matrix, you can always prove it using just the rules that are on this slide. In the interest of time, I will just show you that this is a proof that works in all prime qubit dimensions, that this is the GHZ state circuit on the left-hand side, and on the right-hand side, this proves that it's symmetric in all 3 inputs. This is the final diagram that you get. And I just hint a bit at one of the 3 papers I published on Qtrit compilation this year. This is was at the conference on quantum physics and logic. This shows that if you take this qubit ZZ interaction gate, so then if you do the same thing in Qtrits, you can get a cool gate you can extend this qubit tricks on building control gates to Qtrits, and we built any type of controlled phase gate in Qtrits, and also any type of multiple controlled phase gates. And I'll leave you guys on 2 results. I'm sorry, I'm a bit too excited. I'm just gonna wrap it up quickly. One result is that very recently, I realized that you can do qubit multiple control Tofflees tricks, building a big Tofflee out of smaller Tofflees. We figured out how to replicate that result for any qubit dimension, as shown here. And then you can also build multiple control gates for all qubit Cliffords and even qubit T gate. So this is the qubit control, multiple control T gate. So controlling on any trit string of the inputs. And so yeah, I'll leave you guys on this theorem. So thank you all for listening to my talk. And if there is time for questions, I'm not really sure, but let me know. And if you have any more questions, you can reach out to me on Discord. I'll put it in the chat. Feel free to, or email. Thank you.
Yeah. There are any questions? ¿Hay alguna pregunta en el chat? Also, I share the register form. Voy a compartir la forma de registro para los asistentes. ¿Alguna pregunta? They love your comments.
Thank you.
Ahorita el momento de preguntar es ahora no muchos. Un segundito. Enseguida le envío el formulario, no se preocupe. ¿Hay alguna otra duda, una pregunta sobre la presentación? Okay, well, if there are no questions, we'll give a big clap for Leah. And also, happy birthday, Leah.
Oh, thank you so much. Thank you.
That was a great presentation.
Thank you, everyone. And enjoy the event.
Okay. Enseguida les mando la liga de nuevo para el registro y a las 10 continuamos con nuestra siguiente presentación. Aquí vamos a estar conectados. Bueno, en unos minutos de comenzar, esperemos un momento, enseguida nos conectamos. Hello, Vital. Ayudar.
Hi, Mika, how are you?
Hi there, I'm good. How are you?
All good.
Hello, Vital. Ayudar.
One moment.
Okay, we're going to start in a moment. Let me present you. Ok, buenos días a todos. Vamos a continuar con la segunda práctica de coloquio. En este caso,
Hi there, I'm good. How are you?
okay, nuestro expositor es Mika, líder tecnológico de Quantum Software Team de Zapata Computing. Ha trabajado en la escritura de software científico para el cómputo cuántico y diseño de definición de algoritmos. En este caso, tenemos un pequeño eco. De Quantum Software Team de
Está cerrado tu micrófono.
Perfecto, ya pusimos lo del eco. Mika, when you want, you can start.
Okay, great. One moment. Okay, can you see my screen? Yes, great. So, hello, everyone. I'm sorry, I'm not speaking Spanish, but I can speak Spanish, so I will speak English. Thank you very much for having me here. Really glad to be able to share some of my research with all of you here. So yeah, today I wanted to tell you a little bit about the research project that I've been working on for the last couple of months. And so, okay, a question is, I look at the program and I think I'm the first person that will be talking about QAOA. So, okay, so I'll try to do my best when it comes to explaining kind of what QAOA is, but I also won't get into many details, but we'll see. So, okay, I'll first tell you a little bit kind of a background of what we've been doing, what the tools we've been using, and then a little bit about our research. And okay, so also I think you have introduced me, but I didn't understand that. So just in case, I'm Michał. I work at Zapata Computing, and I'm a tech lead in the quantum software team. And most of the time, I'm writing software, but sometimes I'm doing some research on the side, and this is the effect of that. And I've been very interested in variational quantum algorithms for the last couple of years, and especially QAOA. So there's like a lot of mysteries in these algorithms that bug me. So first, what is QAOA? And I don't want to explain for the 100th time, what QAOA is in details. So I will just deal with the information that I think is necessary to understand what we are doing. If you don't know QAOA, don't worry, you don't need to understand that much of this algorithm. By the way, do you see my mouse? I just want to make sure that, okay, good. So what is QAOA? So QAOA basically is a variational quantum algorithm, which we use to find the state of
Entonces, se resuelva pronto ahorita la confederación. Estamos checando a nuestro invitado.
No, I'm sorry. I think I got disconnected.
No worry.
Okay, I'm back. So I hope my screen is okay. So QAOA, right, is this algorithm where we so we start with this initial state, and then we apply different operators. And what's important in QAOA is first that we do that in layers. So we have one layer of those like U, C, and UB, right? And then next one, and there's like P layers. And another important feature, which as it turns out is rather from current state, which as it turns out is rather like maybe not very typical for variational quantum algorithms, is that actually what we have, the way we construct our circuits depends on the problem that we're trying to solve. So there is this C in here, and this is cost Hamiltonian. So this is the Hamiltonian which defines the problem that we are trying to solve. And we use this Hamiltonian to kind of create the circuit, which gives QAOA some kind of interesting behaviors that that some other ansatz don't have. And we have two parameters here, gamma and beta, right? I mean, two kind of vectors of parameters, because we have as many gammas as we have layers, and as many betas and we have layers. What this kind of B Hamiltonian is, it's like not really important for us. What's important for us is that we have this cost function. So QAOA is associated with the cost function that we can optimize by minimum of. And basically the cost function is the expectation value of the Hamiltonian, cost Hamiltonian, and the state that we have prepared. So the cost function depends on the parameters gamma and beta, and only them. So this is nice because it allows us to, even if our problem has like bazillion kind of qubits, then we still have only 2 parameters, or like 2 times p parameters that we have to optimize. So that's, shortly what QAOA is. And it turns out that for the QAOA with, just quickly about Hamiltonians. So QAOA works only for Ising Hamiltonians, which are diagonal Hamiltonians, which only have like z terms, right? And the Hamiltonian can be so-called like k-body, or like it can consist of like k-body terms. So if we have, for example, a term which is like z0, so z operator acting on 0th qubit, then this is like 1-body term. If it's like z0 times z1, it's 2-body term. If it is z3 times z4 times z7, this is 3-body term. So for Hamiltonians with up to 2-body terms, we actually know, and 1-layer QAOA, we have analytical formulas for the cost function. And basically this is how the equation look like. As you can see, there's like a lot of sinuses, cosinuses, and stuff like this. Kind of parsing it is hard, but it's important that like we actually do have these equations, and I will get back to this a little bit later. Another kind of piece of background is OrgVis. So some time ago, last year, we have published, with people listed here, we have published a paper about performing visualizations in high-dimensional kind of spaces. And we also created a package for this called OrgVis. And if you don't know it, I highly recommend to check it out, both package and the paper, because I think it's like, nice, especially for people who like to visualize things and think about things, in a more visual rather than just like maybe theoretical way. And it's not maybe directly connected to what we are doing, more in the spirit of like we've been trying in our research to do kind of better visualization and get better understanding. So we are not using all the methods that I described here, but I wanted to show it to you because I just like think it's pretty cool, and to give you the idea how one can gain better insight about the problem they're trying to solve from the visualization. So what we have here is, let's say we tried to solve some optimization problem, right? Find the minimum of a cost function with some optimizer. This example has nothing to do with quantum computing yet. And what we did is we ran, optimizer 100 times, and basically we got, mostly we were stuck in like these 2 local minima, and once we were able to achieve this like global minimum, right? So if we make a histogram, we see that, well, roughly, half the time we end up in one or the other local minimum, and then only once we got this global one. What does it tell us about the cost function? What does it tell us about the problem that we want to solve? Well, honestly, not that much, right? It's like, this is something that like most of the time we see when we kind of have to deal with optimization problem, as we do in VQAs, but it doesn't provide a lot of insight. So, what we can do is we can actually visualize how does and this cost function, by the way, is like multidimensional. I think for this example, we use like 6D function, right? So there are like 6 variables. So it's not trivial to visualize 6-dimensional, 6-dimensional cost space. So what you might do is you might find those points where we have like this like one global minimum or the first or the second minimum, and then basically plot how does the cost function looks like when we go in a line, kind of we do interpolation from one to the other, and the cost function changes like this, right? When we go from first to the second, it looks like this, and like between the first and second, it looks like this. We also can visualize, kind of make a 2D slice, right? So basically we take this line that we had here, and then add orthogonal vector and just like plot it. And now, you know, we see that actually, well, this, we can say something about this cost function. Like it seems we are only confined to limited number of dimensions that we are able to visualize here. But you know, these are random dimensions. There's like absolutely nothing special about this like y-axis. X-axis has been chosen by the interpolation. Like y-axis is totally arbitrary. So we see that it's like this cost function looks somewhat spherical. It seems that, you know, there's like some symmetry, that actually there's like plenty of places where we can have a minimum. So maybe actually the second minimum, like first and second minimum are actually like the same. This is like there's some degeneracy, right? So we can visualize it by you know, looking at this path between global and first, like or like first and second. We can actually try to find whether there is a path with like smaller energy. So in Orgvis, we have this thing called elastic band notched elastic band method, which allows you to find what's the path of the lowest energy that connects 2 points in the multidimensional landscape. And basically, if we take 2 minima of the same value, so 2 first minima, right, and we connect them directly, we see that the loss function like increases and then decreases, right? This is on this line. But when we actually optimize this path, we see that, well, it actually is like constant. So what we have here is not really one of like multiple local minima. It's the same minimum, even though the parameters, you know, might be different, like the x and y. So we might think, oh my God, this cost function like so complicated. It's like, you know, we did 100 runs, 50 times it ended up here. It's like it's 50 local minima, and like each is different because every time I look at parameters, I see something different. Well, actually, it's the same. It's like super degenerate minimum, right? But it's like the same value with the same value, which now we have some insight into what the cost function is doing and like how it behaves, and like we can say something about the algorithm we are using. So the cost function for 2D version of this cost function looks like this. We just extrapolated it to kind of 6 dimensions. But you know, it's what I wanted, like the point that I'm trying to make is like visualization is really helpful and really allows to gain insight. And there are like many different, you know, kind of methods for visualization. So now, again, like another piece of background, which is in QAOA, there is something called parameter concentration. This is the effect which Farhi and others showed in one of their papers, which basically says that if we take, I think they took like 25 different instances of like max cut. So by different instances, I mean 25 different graphs, right? So each of them has like very different Hamiltonian, and they tried it for whatever number of layers they checked. And I think these were like 25 qubits, I think Hamiltonians. And they took the same parameters, beta and gamma. So you fix beta and gamma and you evaluate, you know, what's the value of the cost function. So like you calculate this for like different Hamiltonians, like for different C's. And it turns out that actually the results are like very close. So for this particular case, if they found like you know, the low means the kind of the minimum, they optimized it for one instance, and then they took 25 other instances with the same parameters, and it turned out that, well, actually on average they were all had very similar value, right? And the standard deviation of that was actually very small. But when they took like the maximum, it was the same thing. But even more surprisingly, when they took random point in the landscape, so random beta or random gamma, and they used that for like 25 different problems, so like 25 different Hamiltonians generated from kind of 3 regular graph max cut, it turns out that they basically kind of concentrate, the value concentrates. So what does it mean? I mean, it means like they did even more crazy things. So like if you take the Hamiltonian for, let's say, 10 qubits and you find a minimum, and it's pretty decent minimum. And then you take a different Hamiltonian for 20 qubits and you use the same parameters, well, it's still pretty decent minimum. I mean, the value doesn't, change a lot, which is surprising because this basically, the implication of this is that maybe we can solve small instances which are much less resource intensive, and then use solutions for those small instances that are kind of easier to solve, and feed them as like initial parameters for like much bigger instances, and then solve them much quicker. Or it might have like all other kind of crazy theoretical implications. So in Orgby's paper, we decided to actually take a look at that and analyze. This is for, I think, 4-layer QAOA. We picked kind of always, making the 2D slice through like n-dimensional space, and we always did that in the same directions. And it turns out that as you go from 4 qubits to 20 qubits, as you can see, these are like for different graphs, and like, I'm sorry, all good? Okay, someone's talking. Okay, I will just move forward. So please mute yourself, unless you want something to me, like make it clear. So this is Erdős-Rényi graphs. So these are like random graphs, but even for those random graphs, apparently there is some structure, because as we go from a random graph with 8 nodes to random graph with 20 nodes, and even with like random weights, you see that the landscape like preserve certain features. Like there is something going on here that like we don't fully understand. But like this graph for 8 qubits has the only thing that it has similar with the graph for 20 qubits, that it was generated with the same method, right? So that's like it is kind of a mystery, I would say, to like many people dealing with QAOA. And so this was, but we've seen already that this is not about just like preserving value at like particular point, but also about preserving the shape of the landscape, which is kind of one step further, towards understanding what this parameter concentration is about. And the last example I wanted to give you, which is now directly getting into our research project, is, and I can't take questions in Spanish. I'm sorry, but the last question is this? It comes from the research I did on variational quantum factoring, which is that I had like 2 Hamiltonians. Like one is this like super simple 2-qubit Hamiltonian, and you see there's like 3 terms, not much kind of happening. And then the other one is this like fairly complicated. I think it has like 34 terms with up to like 4 body terms, and it's much more complicated. Let's say it has like many more different combinations, like hard to see even like what's the structure. We would try to write it concisely, but it's basically, it's pretty complicated. But it turns out that, and this is for 6 qubits, and this one is for 2 qubits. But when it comes to the cost landscape, it turns out that the cost landscape here is kind of harder. Like intuitively, we see that it is harder than the other one, right? Here we have a lot of local minima, local maxima. It's like very rugged, and it's very rough, and it's easy for the optimizer to stack in some of the local minima. Here we have pretty nice structure. That there is something happening over here, but basically there's not that much kind of local minima, not as many local minimas as in the other picture. But this Hamiltonian is like so much simpler than the other one, and it has lower kind of k-body terms, a smaller number of qubits, and like intuitively I would say like this landscape should be more complicated because it comes from like way more complicated Hamiltonians. Like what the hell is going on? And that was the kind of motivation, one of the motivations for this research. Question: is everything all right? Or
yes?
Okay, good, because I see some movement on the camera and like I'm not sure, so just wanted to make sure. Okay, so tools, like in order to try to explore some of these questions, we had to come up with some tools. So, and before I get into the tools, who was actually involved in this paper? So this is the effort that I started with Laura, who was interning at Zapata for some time. Then later, actually it started as two separate projects that we later merged. So I started a project with Laura and separately a project with Yogi, who also has been intern at Zapata, and we later merged this into this project. And we also involved Manuel, who was the main author for Orgvis, who was working in Zapata. Now he's doing PhD at EPFL. And while I was working with Laura on Fourier analysis, getting to that point, I'll tell you more in a moment. I've seen a presentation at a conference from Enrico, who turns out also is tackling, was analyzing the QAOA from the perspective of Fourier analysis. So we joined our forces, and Enrico has been helping us with this project since. So Fourier analysis. Again, very shortly, what Fourier analysis is where we take some function and we try to figure out, decompose it into its base frequencies, right? So if we have a function like this, we can calculate what kind of frequencies make this function. So it turns out that in this case, this I think is like cosine x plus cosine y. And we see cosine 3x plus cosine 3y. So, and we can see kind of this in the Fourier plot, where you see that there is one frequency component going in for x direction, right? It has 0 in y and just x, and it sits as 3. And then similarly, it's 3 in the y direction. And as you can see, there's 2 pi period, and we have it's for a 2 pi extent, and we see that there's 1, 2, and 3 repetitions of the same. So the frequency is 3. The period is 2 pi over 3. And Fourier analysis is cool because it allows us to analyze the kind of problem that we have, the function, the cost function, from a different perspective. And as you might know, a lot the cost functions generated by quantum circuits can be described, especially variational quantum circuits, can be described as combination of trigonometric functions. So to make the point even clearer, if we get back to this, which is analytical formula for the cost function of QAOA, there's nothing but cosines and sines of beta and gamma, basically, with different coefficients. So, and also if you look at this plot, it seems that there is some frequency to this movement. So we thought that well, maybe this is a good tool to analyze those cost functions. So if we do this again, very, very basic sine plus cosine kind of function, it looks like this. If we take QAOA, very basic QAOA, one layer with the Hamiltonian Z0 plus Z1, this is how the cost function looks like. And we can see that, well, this is basically something like cosine 2x, so cosine 2 beta times cosine 2 gamma. Because this is how you would read this Fourier plot. These Fourier plots that take a little bit time to kind of get used to how to read them. But basically, if you see you see this component at at 2. So if this is the how to say that, basically the plot here is, it's frequency of beta and frequency of gamma comma frequency of beta. This is what every point on this plot is. And if we take a more complicated kind of Hamiltonian, like this one, we can still, plot what the result is. But you can see that since we have non-integer coefficients here, it means that the frequencies are also non-integer, which makes discrete Fourier transform a little bit more tricky. So we end up with not all the peaks being like so clear, right? So you notice that like here we have like 1 pixel here, 1 pixel here, but here like some of those pixels are actually not pixels anymore. They're like more distributed. And by the way, I'm sorry for the quality of these plots. We still haven't published this, and we're like working on putting it on archive. But so all all the plots are like work in progress. That the labels are not exactly what they should be, but we're just like finalizing it and trying to put it on archive. And we haven't redone all the plots because well, that kind of wasn't priority yet. So sorry for that. What you can see here, for example, that not only some of the peaks are kind of like non-localized, but some of them are also like kind of smeared. You can see those artifacts here that like long tail. So this usually comes from the problem with resolution. So if we take a landscape as we see to the right, and we start doing it for a resolution of like kind of 20 samples, we get something like this. As we increase the resolution, the picture gets better. So basically, there are like a couple of, when it comes to this Fourier analysis, there are a couple of like technical issues where sometimes those artifacts are coming from the resolution. Sometimes actually resolution is not the problem. They're coming from the fact that, well, fundamentally the coefficients are non-integer, and that's just the distribution you get in such case. So there's like a lot of like technical nuance when it comes to performing analysis like this. So this is like Fourier analysis is one tool, and you will see a lot of those Fourier plots later on. Another are metrics. So remember this plot here. I told you that, well, this landscape is like more complicated than the other one. Well, but like how do I say so, right? I mean, intuitively it makes sense to me because I did a lot of optimization in my life, and I know that with this number of local optima, and like being them, like those optima also being like so deep, right? They're like there's like from -4 to 8 basically here. So there's like very, very steep optima, and like this is confusing for like a large family of optimizers. Well, here we have the differences are not so big, and etc. So I can see that as a human, but like how do I quantify that? Like how do I say whether this is more complicated than like the picture we've seen before? So we tried to define metrics, and we used basically two metrics. One is called roughness, and it was defined in this paper where they've been analyzing actually the loss landscapes of neural networks. So it had nothing to do with quantum computing. It's like just neural networks. And if we have two cost functions like this, so this is basically like some pure sine, and this is sine with like some extra noise, and we take derivative, like absolute value of derivative, and then integrate that over kind of this period. Well, we'll not have the derivative of this function will be smooth, nice, and like nothing big. Here the derivative changes a lot, right? So we can capture this change in this equation, right? Because this is how much, like how quickly was the function changing throughout, like from A to B. And well, this is kind of one of the metrics that we used, and the other is called Fourier sparsity. So okay, so Fourier sparsity basically measures like how many components you have here, or like, and how strong those components are, right? So if you have a landscape like this with only one peak here, it has like lower, like kind of lower Fourier sparsity than this one, because this one has like many more dots here, many more components. And apparently there are like some theoretical arguments you can make to calculate this easier. We have tried a couple of versions of this matrix, calculated in different types. In the end, it turns out that if you take the one, like basically this matrix can be described as 1 norm squared over 2 norms squared of the vector of Fourier components. Honestly, there's like some theory magic going on here that like translates what I intuitively said, that number of peaks in this plot, you know, being like not many peaks to a lot of peaks correlate with this particular equation, and we explained that in the paper. But so if you are interested in this detail, you will have to wait until we put it in an archive. But anyway, with this tool, so like basically 2 main tools that we introduced here, or like maybe reused, are Fourier analysis and also those metrics. So now I would like to show you some of the results we were getting. And I'm just sort of looking at the time. Okay, we are good. I will try to finish a bit earlier to give you time for questions. So first we started from, or maybe actually at this point, do we have any questions? Or is there anything particularly confusing or unclear?
¿En el público hay alguna pregunta? I think no. Okay, you can continue, Michael.
Okay, okay. Great, thank you. Okay, so we did some research on this, right? And we try to understand, you know, what makes certain, why certain Hamiltonians produce very hard cost landscapes, while some others produce not very hard cost landscapes. Where does it come from? What influences this behavior, etc., etc. And for our analysis, we used only 1 layer QAA. So everything you see is like 1 layer QAA. So there are only 2 parameters, 1 beta and 1 gamma. And we started with a very simple Hamiltonian. We started with Hamiltonian, which has basically this form. And this is, so it's like Z0 times some coefficient A, Z1 times some coefficient B, and, you know, like Z0 times B1, like times some coefficient C. And what we've been doing, we have been changing the A, B, and C. And why did we start with this? Well, first, because it's very simple. And, you know, if kind of our tools, our software is not working, then we'll probably be able to debug it much better on a simple example like this, rather than, you know, 20-qubit Hamiltonian with like bazillion of terms. Second is that we actually know what are the analytical formulas for this. So if we take the equations I've shown you before, right, and we actually substitute all kind of numbers into these terms, we get something like this. So the cost function is the sum of those like 3 kind of smaller functions. And basically we have, you know, sine of like 2 beta, and then here is, so this part is like dependent on beta, and this part is kind of dependent on gamma. So we have like sine of like 2 gamma A times 2 gamma C. And here, similarly, you just see that A and like A's and B's are replaced. And then for the kind of the term kind of associated with this Z0, Z1 term has this like kind of more complicated form that you can see here. But now that we have like this simple example, just by inspecting this, we can already see a couple of interesting features that, well, I would say were totally not obvious to me before I started looking at this. So first is that actually, if you look at all the terms with beta, they are not parameterized by the shape of the Hamiltonian. So the beta part, right? We have like sine of 2 beta, sine of 2 beta, and like sine of 4 beta, and like 2 beta squared. Which means that all the frequencies in the, because what we multiply beta by dictates the frequency, right? So we'll have only components with the frequency of 2 and 4 when it comes to like beta dimension in our plots. So in kind of one dimension, the choice of our Hamiltonian, at least for this toy problem, right, like doesn't influence at all the cost function. For regardless like what parameters we have, we will always have kind of the same components in beta direction. So what's actually interesting is this gamma direction. And as you can see, first is maybe here that we have those components with a plus b or a minus b. So we see that actually it's not only important what are the values of a and b kind of in isolation, but it's also important what's their relation, because if they are the same, so like a equals b, then like we have one less term in the overall picture. Or if they're like, the opposite. Also, we see that actually what, if they're like both big, then like we'll have this, let's say like a is equal to 10 and b is equal to 10. Even though this term here will disappear, then we'll have something with frequency of 40 coming from this cosine. So 40 means like a lot of oscillations, right? Like very crazy landscape. So this is something that's like kind of interesting to just like looking from equations. And I will show you this in the plots in a moment. Like another thing is that those coefficients, they not only go into the frequencies, but they also go into the magnitude. So as we increase any of the coefficients, it means that both the magnitude and the frequency are changing at the same time, which makes those functions kind of harder to analyze. There's like some other things, but let's actually look how it looks like in practice. So what we can do is, if we take a Hamiltonian where we say a equals b equals 1, and then we just change c, we can actually calculate all the frequencies that we'll see in the plot. So for c equal 1, as you can see here, we have this pretty nice landscape, and it's not very complicated. As you can see, it has like 5 terms here, right? So like it has five components, like 1, 2, 3, 4, 5. And we can actually find these components here. So there is this like 4, 2. So this is 4, 2, like these are like coordinates in this plot. It's like 4 and 2, this is 4 and 2, right? We have 0 and 4, so there's like 0 and 4. There's like this component here, and like 4 and 4 is like 4 and 4 is here. So we can exactly predict how this will look like. And as we only change this c over here, we see that, well, some of the like some structure of this Hamiltonian, like some structure of this cost landscape stays the same, you see, because in every picture we have roughly the same components kind of here in on the left. And then there's like another group of components that is moving towards like right. So as you can see in the plots, like when we have these components here and we move them to the right, this means that the frequency, this is gamma, this is beta, like frequency in gamma is increasing. So here you see that like in this period, we have basically kind of 1 and 2, right? Like we kind of repeat ourselves twice. So the frequency is, well, it's 4, but like, you know, it's kind of fits twice. But as we go to the right, the frequency increases, and we see that, well, there's actually much more going on here, right? And here even more. So this is for like 20. So we see that like when we have this number 20, there is like 40, the frequency is 40. So like in one kind of, well, over the domain of 2 pi, we get like 40 repetitions of those, like for these terms. But on top of that, you can see that there's those low frequency terms as well, right? That give the overall structure to this picture, because you can see that there is like some global maximum here, right? And like some global minimum over here. I mean, not global, but like behind those high frequency ripples, right? And similarly here, there's like, this is the same feature that you see in like all those places. So like, even if you add more frequencies on top of this picture, kind of some structures still persist. And, you know, these two are like kind of independent of each other, right? Because these two apparently are independent of the C. And, well, like these components here and these components here are actually changing with increasing C. Okay, so what we did, like another thing we did is we took, oh, also another, if you see, like there is this like roughness index. As I said, we did like a lot of iterations with exactly how to calculate this metrics, because you can normalize them, you can not normalize them. There's like different ways to calculate them. But as you can see, let's look at this number roughness index, this one. So this is like very low. It's like 5 for this like simple landscape. And it's like 23 for this complicated landscape here. And as we go to more and more complicated landscapes, we see that this metric actually increases, which is good. Like this means that basically these metrics work. And the other metrics as well. So it starts with 8.5, and then it goes to, you know, almost 17, almost 19, 25. Another case that we analyzed is with random coefficients, Hamiltonian with random coefficients. So basically we created like a lot of plots and tried to see whether we can see anything interesting here. And for example, it turns out that actually the fact that we have integer or non-integer coefficients is like having non-integer coefficients doesn't make the problem kind of more difficult by itself, right? As you can see, here we have two landscapes, one with some random coefficients, and then we rounded them to the nearest integers. So if you look at these plots, you can see that by changing the coefficients a little bit, you actually, well, these are two different landscapes, but like some features here are preserved, right? And basically the kind of, if we also check when you just like change those coefficients a little bit, then the changes are gradual. It's not that like suddenly when you move from like integer to like from integer coefficients to like real, and like suddenly those landscapes are much more crazy. But interestingly, like the Fourier spectrum actually gets much more crazy, right? Which kind of makes it much harder to analyze. And we tried this also on like bigger Hamiltonians, bigger plots, but in the end, we stick only we decided it's worth discussing for those like random weights only for the case with the toy problem, because it's not that different and it's just like easier to analyze. So the next thing we did is we went into 6-qubit Hamiltonian. So 6-qubit Hamiltonian is interesting because A, it's bigger, but also it allows you to go beyond 2-body terms. So you can have you know, Z0 times Z1, but now you can also have Z0 times Z1 times Z2, Z3, Z4, Z5. So have like 6-body term, and you can analyze how those like higher kind of higher order terms influence the landscape, whether it actually makes the landscape like way more complicated, or maybe it doesn't matter at all. So what we see here are some Hamiltonians that we analyzed. So basically, these are all the possible one-body term plus all the possible two-body terms. Then all the possible one-body terms plus all the possible three-body terms. Again, one-body terms plus four-body terms. One-body terms plus five-body terms. And as you can see, well, actually, having higher body terms, that doesn't really makes your landscape like, I mean, doesn't determine your landscape to be much more complicated, right? So you can see that, for example, here, well, this landscape is just kind of has pretty clean spectrum, right? It's like much cleaner than this one, even though it contains like higher body terms. Okay, like there's like a bunch of other things, but one particularly interesting results that came from where we try to look more into the parameter concentration phenomenon. And we've seen that for when we took like maxcat for 12 qubits and maxcat for 20 qubits, actually you can see that the landscapes are very similar, right? So this is kind of, it shows kind of parameter concentration. Same for like Erdos-Renyi graphs, or like random graphs with random weights. Again, you can see that those landscapes kind of converge, you know, when, like I didn't show like all the intermediate results, but like they get to converge to something. But you also can see how they converge in the Fourier spectrum as well, which is interesting because they form this distribution, and like the more qubits you add, the more this distribution kind of is nice and like well behaved. And also those smaller frequencies here with this component kind of tends to be, you know, less visible in here. Okay, so basically to wrap things, okay, this is crazy. I had to show you this. Another thing which is super weird is that we had a Hamiltonian with this, like we called it qubit path. So Z0 times Z1 times Z2 plus Z1, Z2, Z3, and so on up to like, for example, 20 qubits. And it turns out that this is the case for like the nice Hamiltonian, but if you drop one term, so it has like some structure. If you drop one term, then suddenly you get a picture like this. Or if you increase one term, like weight of one term to 50, then like it gets into something like this. So even changing one term, in some cases, changing one term doesn't change much. In some cases, changing one term just like makes the whole landscape look crazy. So we analyzed also the initial example. And okay, given I don't have much time left, I'll just like jump to the conclusions maybe. So we try to answer the question like, what makes Hamiltonian more complicated, right? And number of qubits doesn't necessarily make them more complicated. Number of terms as well. You can have a small number of terms, and then you can have, but still have very complicated Hamiltonian. The order of terms does influence it a little bit. So as I showed you here, it doesn't necessarily make it much more complicated, but for two-body terms, we only get up to kind of frequency of 4 for beta, and then as we go, we get like higher and higher frequencies here. So it like influences like might be more complicated, but not necessarily. What does influence are like what weights do we put? If we have like one weight with like very high weight, it will end up adding like some super high frequency term, which will just like wreak havoc. And also the structure, and structure is like very elusive because I have no idea what it means. I mean, like literally, like this requires more research. How do you define the structure, and like what are some features of the structure of the Hamiltonian that like make certain landscapes simpler or more complicated? Another question is we try to answer is Fourier analysis useful? And like totally, it just like allows you to see the world of the cost function from like very different perspective. Are metrics useful? Yes, they are useful. I didn't get, for the sake of time, too deep into how metrics kind of behaved, but there are like certain cases where they behave very well, and there are like some others where they were like surprising. So I would say it also like requires a little bit of more kind of research, maybe coming up with like some other metrics that are better defined. But in general, like looking at it from the perspective of metrics was useful. So two things that we know we didn't have time to put into this project, but are definitely important questions is first, what happens when you have multiple layers? This is all in one layer QAOA. So basically toy problem QAOA. And we have some methods to visualize in like higher dimensional space. So we basically know how to proceed. We just kind of want to close this part and then move to the next one. And the other is like how metrics do metrics predict the behavior of the optimizer correctly? Like, because if the metrics correlate well with how the optimizer works, this is really important because it might allow us to just be able to predict from the Hamiltonian whether the problem will be hard for the optimizer to solve or not. So that would be pretty cool. Where to learn more? I really hope we'll get the paper on archive by before Christmas. I have a blog where I write about like different things like quantum computing, and like I have some career related content there as well if anyone is of interest. And so you can find me there. And also I recommend checking out our OrgVis library because just go there, play with that. It might help you with some of your projects. So thank you very much. I hope I'm not terribly over time. And do we have any questions?
Thank you, Miguel. Any questions? You can ask in English and Spanish. We translate the question. Also, I share with you the form to register to the event.
Hi, Michael.
Yeah.
This is Moises here.
Hi there.
I'm not sure if, seems to me that you were modifying several parameters, like the number of qubits, the roughness, I think other parameter. Question is, did you make experiments fixing at least two parameters and varying one?
So I would say that one thing that one thing is number of qubits, for example. Another is a structure of the Hamiltonian. Another is coefficients. And yes, we did that. So for example, there was this one experiment where we just change the values of the C parameter here, right? And analyzed how this influences the landscape. In another one, we just changed, we kept the number of qubits fixed, right? And we just changed how does the Hamiltonian looks like. And it was always with like unit weights. So the only change that things was like, what kind of terms do we have? We also did like another experiment that I didn't have time to go through, but where we took Hamiltonians and we just like were adding terms one by one. So coming from Hamiltonian, well, that was basically only one body terms to all the free body terms. Yes, in this case. So yeah, sure, we did this kind of things.
Okay, thank you so much.
Thank you so much.
Congratulations.
Oh, thank you.
Thank you so much, Miguel. And we have a big clap for you. And your presentation is an excellent work. I think it's very important to work in optimization paradigms using quantum computing because it has a lot of applications, especially in AI and other data extraction problems. So thanks so much for the presentation.
Thank you very much.
Also, we need to close this chat because in 3 minutes we have the next presentator. Thank you so much again, and we see you in a minute. Bye.